and get started. All right. So linear and logistic regression are both techniques that are used to predict an outcome of some kind. So basically, you provide it with a series of variables that are your independent variables, and then it'll predict some outcome, your dependent. And depending on if you're looking at a classification problem, i.e. trying to categorize things into something, who knows what your categories are, right? But you could have that, or you could try to predict a continuous output, like say, the price of a given item or something like that. And depending on which one of those you're doing will determine whether you're using linear regression, which predicts continuous outputs, or whether you're doing logistic regression, which will do categorical ones. Right. So I do have a series of packages we're going to be using today, and I'll walk through those pretty quickly. So, of course, we have our standard ones like pandas and NumPy for basically messing with the data itself within Python. But we also have this new thing that we're looking at called train test split from sklearn. So sklearn is a pretty important package as you go forward into machine learning applications, and even for linear and logistic regression, because almost everything comes from there. But what train test split does is pretty much do exactly what it's titled. It'll split your data into a training set and into a testing set. And what each of those do and what they mean will become clear a little later on, but it is a new thing that we're introducing for this lesson. Right. And within linear regression, there are a few things we're going to do. There's a statistical summary, a model, and the model results. And pretty similar for logistic regression, except that you don't have that statistical summary. And we are going to be doing a visualization as well, because we are going to explore how this applies to forecasting, as well as some other things. So it's very important for BI applications as well, business analysis, business intelligence, etc. So of course, we get our data into Python and all that. That's pretty standard. Although for this week, we do have two data sets that we're working with, because the Airbnb data that we have does not have any time information. So for us to do a forecast, we need time information. So I just created some data that is a time series for us to do forecasting with. Right. So linear regression, again, can predict a continuous output, and it can take almost any kind of predictor that you give it. So this is really important because you can give it both a continuous input and a categorical one, even an ordinal one, which would just be like something over time, like in a time series. And that's important because a lot of other models will only allow you to work with one kind of predictor. And because this is able to work with multiple, it makes it really good for reducing the number of features that you decide to include in your analysis. And it allows you to work with predictors that you might not be able to work with in other models. And oftentimes, those will have more impact than you think they do, right? So the ability to mix those together is pretty important, even if it's just a stepping stone towards getting into other models. Right, so as I kind of alluded to, linear regression can be used in a few different ways, namely reducing the number of features that you include in your models, predicting a continuous outcome, and forecasting. So one thing to note about linear regression and pretty much any kind of model you would use, including logistic regression, if you have a categorical input, that is one of your independent variables is categorical, you have to encode it into binary for Python to be able to work with it. Because it doesn't fare well with text data, you just have to convert it into binary and then it'll be fine.
Yeah, like yes or no, 1 or 0, something like that, positive, negative, something like that.
Exactly. It'll just code everything into ones and zeros.
Oh, okay.
Right. And that's pretty easy to do. You can just do this command here, pd get dummies, and you can specify whichever columns you want to create those binary variables for, and then specify the data you want it to work with. I need to go up and run a few cells just so that we're all able to see how this runs as we go through.
Max, are you sharing your screen?
Yes, can you see it?
No, we can see it.
You cannot see my screen.
Yeah. What about Ryan?
I can see your screen.
Huh.
I can see your screen. I can see it.
Ah, okay.
Okay, that's strange.
1 minute.
Let me move my things around. It does say that I'm sharing it, and Ryan is able to see it. So I'm not sure what's going on there. Do you see a file called linear and logistic regression opened in Chrome, Rujan?
Give me a moment. Yeah, I think I can. Yeah, now I can see. Yeah, I can see.
Okay, you can see it now. Okay, good. Good.
Thank you.
All of this down here is just me installing something called DMBA, which is needed for the model results, but that's not too important right now. I'll just load in my data so that we can run all these cells as we go down, and we can see what is happening in the outputs. Right. So here I have my Airbnb information, and I know that I have these things like neighborhood group, neighborhood, and cancellation policy, which are categorical in nature. And if I want to use those as predictors, then I need to encode them into binary. So you would say get a binary for cancellation policy is strict. And then it would be a 0 or a 1, depending on if it's strict or not. And you would get a separate one that would say whether or not it was moderate. And it would have that for every possible entry in the cancellation policy. That's pretty much what get dummies does. And it'll do that for any column that you specify. If you don't specify the column, it'll look at every column that is an object, aka is a string, and create a binary encoding for all those possible entries, which is not always a good thing. Because you can see here, you have house rules way at the end, and those are probably going to be different for every single entry in this list. So if I did get dummies and I included that column in get dummies, I would just have like an extra 100,000 rows or extra 100,000 columns, and that's not useful to us. So just doing get dummies without the columns parameter would be a bad idea in this case. So I just managed to specify which ones I wanted to use. And in this case, those were neighborhood group and room type. Right. So what I'm trying to do in this particular regression is see if we can predict the price of an Airbnb listing based on whether or not the host was verified, the neighborhood it occurs in, the cancellation policy for the listing, the construction year for the listing, the service fee, and the house rules. Or at least those are the columns. Oh, no, those are the columns I'm dropping. I apologize. It's been a little while since I reviewed this, so. Right. So Airbnb info. Okay, this will show me what I'm looking at here. Right, so price is our outcome, and our predictors are the number of listings, the neighborhood group, all the possible entries for it, and the room type, all the possible entries for that. So pretty much, what neighborhood is it in, what kind of room is it, and how many listings have there been at that given listing, using all of that to try and determine the price. Right. Python really does not like working with column names that have spaces in them, so it's always a good practice to rename any ones that do. Like in this one, I see like Staten Island has a space, so I just rename it to Staten Island with an underscore between it. Pretty straightforward. Just make sure you do that so things don't get confused in the program. So that's been renamed. So this is a statistical approach to linear regression, and it's probably the most traditional in that you will see it in stats classes and in plenty of other disciplines, because this will look at your data as a whole and see how well these things can predict your outcome. This is not looking at a subset of the data or anything like that. This is looking at everything. So if I run this, I will get a summary report at the very end of it. If you look at this formula, it's basically the price and how it is determined by all of our inputs added together. And it takes it from the data Airbnb 3. And it provides the summary at the end of it. So there are a few things we need to look at to see how well this model performed. And those are the adjusted R-squared, possibly the R-squared, depending on the situation, and the p-value. So if you were working with just one predictor and one outcome, then you would look at the R-squared, and that'll basically tell you how well the model performed, and if it's close to 1, then it's done well. And same thing for the adjusted R-squared, except that you use that if you have multiple inputs. And as you see here, the adjusted R-squared is terrible. So it did not predict it well at all. But what we can see from here, using the statistical summary, is see which of these inputs were more relevant to the price outcome. And we can do that by looking at the p-values for each of these. So what you normally try to find in a p-value is something that is less than 0.05. Basically, that indicates, okay, p-value basically indicates the probability that the impact that this variable had on the outcome occurred by chance. So if it's a high probability, that means that the difference that it makes on the outcome could be completely random. But if it's low, that means, okay, there's probably a decent correlation here. And as we look through this list of p-values, we see a high p-value, high p-value, high p-value, until we get to the room types, where they're all at value 0, at least within this model. And that can suggest to us that the room type, is important to determining the price. And this is what I like to call feature reduction, because now we know these are the features that are relevant, and these are the ones we should consider going forward. You can get rid of the other ones for now and just use the ones that we think are relevant and see if that improves the model or not. And here, I'm going to do the same thing, except I'm only going to focus on these room type and see if that helps it at all. Right, so now I only have the room type columns and the price. And I'm going to generate that statistical summary again, just to see if it improved anything. So looking up at the R squared, no, it didn't. So really, the inputs that we gave it, none of them were able to predict the price well. But we wouldn't have known that if we didn't run these tests, right? And same thing with the p-values. They're still higher than we would like to see, because again, we would like to see 0.05 or lower, right?
Yeah.
So yeah, it still cannot predict price. But that is basically a way to do feature reduction through that statistical summary. But if you're wanting to do a model instead, then it's going to look a bit different. The difference between the model and the statistical summary is that the model will be able to predict data or predict the outcome with data that does not have that outcome already labeled. So say that we have a model and we train it on some data that already has the price with it. It'll be able to learn from this data and learn how to predict that price. And now if you run that model with new data that does not have the price, the model will be able to predict the price. So one application for this in this case could be like telling people who wants to add a listing on Airbnb what price they should have based on their location and the room type, right? So here, the way that machine learning typically works is you will have a training set and a validation set. The training set will basically include data that the model is going to learn from, and then you'll have your validation data. And that data will be used to basically run your fitted model on, and then compare what the model thinks the output should be to the actual output. And then you can look at some error statistics to see how well it actually predicted the outcome and determine whether or not you should use that model on unlabeled data. And there are several error statistics for that, so we'll just go through here. So here, this is pretty standard formatting for any machine learning application. Basically, you have your model, you fit it to your training data, you generate predictions for the validation data, and you will create a result set, which basically shows the actual output, the predicted output, and the residual, which, as you can see, is just the difference between the actual and the prediction. And here I'm creating a box plot of the residuals, because if you have outlying residuals, say like way up here, then you need to use different summary statistics to gauge the quality of the model. So generating that box plot will tell us what we actually need to look at. If I print my results, I can see my predicted value, the actual value, and the residual. And we can see they vary quite significantly. So that already suggests that it's probably not done well, but we can generate our error statistics here. And this is provided in the package provided in the beginning of the file. Basically, it'll just generate summary statistics looking at your validation and your prediction. And this will provide a series of statistics, mean error, root mean squared error, etc. If you have outliers, then you want to use statistics that are less sensitive to them. And those, the ones that are less sensitive, are the MAE and the MPE, the mean absolute error and the mean percentage error. However, this one does not have significant outliers, as we saw in the box plot. So instead, we're going to look at the root mean squared error and the mean absolute percentage error. So the mean absolute percentage error is easier to understand because it's literally just a percentage of how much your data differed from the actual value. And the root mean squared error is instead scaled to the scale of our data itself. So you have to be familiar with what your data looks like to use it. Root mean squared error is the better metric, but you have to be careful when interpreting it. But here we see like the root mean squared error is about 332. And if we look at our data, the actual values, that's very close to the actual values, which means that these residuals are almost the same value as the data itself, meaning that it's all over the place. It does not know how to predict this. And the root mean squared error suggests that it has an error of over 100. And that's horrible. So this has not performed well at all, as we would expect from the statistical summary. But what this would tell us is that we, at the very least, should not use this model to predict this outcome. There are other models which might perform better, but this one did not perform well. And in a forecasting situation, more business intelligence, you have to do your training and testing a little bit differently. And the situation where you can apply linear regression to forecasting is pretty limited, at least if you're following best practices. And what I mean by that is linear regression, of course, will provide a linear output. So it's just going to go in a straight line. Whereas forecasts and actual time series data is usually all over the place. So, for instance, if there are regular patterns in your time series, say like you often see higher sales on Saturdays and Sundays, then a linear forecasting model will not be able to show that in your future forecasts. So if you know that's present, then this is not your best option. But if there are no patterns like that you can tell, and you have a regular trend line going through the data, then linear regression is a good option. And that isn't to say that you can't apply linear regression if there are these patterns. It's just that it's not the best thing you can use, if that makes sense. And forecasting is a little bit outside the scope of what we're going to teach this semester, but this is one approach to forecasting. Right. So of course, we have our data. We have about 10 years worth of day-by-day demand for something. And all I'm doing here is basically converting it into a date format because it had read everything as a string, aka an object. And now I just converted it to something proper. And I put it in the index. I'll get to why I did that in a second. but it is important. Now, linear regression in Python does not like to work with dates directly. So instead, what you should do is create a new column that increases by 1 for every given row so that it's able to see the order of the data without having to refer to the date. So think of it as instead of like January 1st to January 30th, it's just 1, 2, 3, 4, 5, 6 all the way to 30. Linear regression is going to perform much better on that because it cannot read date information by itself. And what this is doing is basically going back to NumPy and calling upon the range of the length of the data itself, in this case called time. So basically, it'll look at the entire data frame of time, calculate the length of it, and then it'll get every value in that length, 0, 1, 2, 3, 4, etc., all the way down, and put that into the column. And here, I'm just filtering it down to 2 years, so it's a little bit easier to see what's going on instead of the full 10 years. And now I'm going to plot it and see if linear regression is appropriate for this data. And as we look at this, we can see it does have a strong trend line, and it doesn't appear to have any patterns in it. I would not expect to ever see this kind of trend line in an actual forecast, but for pedagogical purposes, it's fine. Just know that. Just know that. But yes, here linear regression would probably be perfect. That's why we're using it. So whenever you split forecasting data into training and testing for the model, you need to do so in a way that preserves the order of the data. So normally whenever you split data, it'll select rows at random to put into the training, into the testing sets. However, because this data has a sequence, you have to keep it in that order. So here what I'm doing is collecting the first 75% of the data in the order that it already is in for training purposes. And I'm doing the same thing, but for the last quarter of the data here for validation purposes. And I do have to reshape them, but that's not too important. Basically, that's Python being Python. But again, we will specify the model we're using, fit it, create the predictions, residuals, and box plot. Again, to see which error statistic we should look at. And here we see there are no outliers, so we should use RMSE and MAPE. And if I print my results, we see the residuals are quite small compared to the actual values of our data. So that suggests it's probably done a good job. And as we generate our error statistics, we see that the root mean squared error is small compared to the actual values of our data, 24 to like 6,000, 7,000. So it's done well there. And the percent is tiny. So it's done an outstanding job at predicting this particular data, which means it is valid to create a forecast. If you got extremely poor results, then you might decide to look at another forecasting method. But here, it is appropriate And we see that through these statistics, so we can go ahead and use it for a future forecast. So this is basically me creating a new data frame that includes our days for the next year. So as we look here, it's going from January 2022 to about October 2023, a bit further than that, really. It's just that's the latest label. So now we're going to generate the entire year of 2024. So I have to make sure that I'm using the proper day number. And I'm also going to add the dates into the index again. And the reason why everything for the dates is in the index is because if it wasn't in the index, it would confuse the model. That's one reason. And the second reason is because putting it in the index allows us to see all of the months and the years as we go forward through the time series, making it much easier to read. Right, let me get back down to where I need to be here. And this will basically run, okay, this here will not run the model yet. This is just showing that the data frame was made correctly. But here, remember, we already fitted the model and we called it LNR. It's fitted to our training data set. So now we can just predict the values for the new data set. So it's already been trained. Now you're giving it unlabeled data to make predictions for. And here we see it now has a column saying, here's the demand, whereas before it didn't. So the model was able to generate some predictions and put them into our data frame. And now I'm just going to plot everything that we've done and see how it looks. Right, so the blue is our historic data, and the red is the forecast that we created. Obviously, this data was very well suited to this particular model, so it's worked well. But again, in most cases, you're probably not going to see this. But it does show us what we could expect to see in the future. And logistic regression, as I was stating earlier, is used for categorization purposes, usually called classification, but I don't like that term very much.
Yeah.
Right. So basically, it'll predict the category that a row belongs to using any kind of predictor that you give it. Again, these models really don't like time series, but that's a different story. And there are two main versions of logistic regression, and they vary based on what the output looks like. There is binary logistic regression and multinomial logistic regression. Binary is used for predicting a binary output. Something like, does this person have cancer or do they not have cancer? And then multinomial would be used to categorize into multiple categories. Like in our Airbnb instance, we have several neighborhoods it could be categorized into. So you would use multinomial to determine that. So here, I'm going to apply binary logistic regression to see if an Airbnb listing is in the Bronx or not. And this is very similar to the way that the linear regression was coded. Basically, you just specify what you want your inputs and outputs to be. You'll split the data into your training and testing sets, clarify which model you want to use, fit it, create your predictions, but at the end, you're going to get a different set of statistics. Remember, we're predicting into categories and not into a numeric output. So you can't do the same kind of calculations for summary statistics at the end of it for this as you could for the other one. So your results are going to look quite a bit different. What you're looking at here is a classification report. And a classification report will basically tell you how well the model was able to categorize into your given categories. This one performed quite poorly, but I'll explain why. If you're looking at a classification report, there are really 4 main metrics that you're looking at. Those are the recall, the specificity, the precision, and the accuracy. And here's what all of those mean and how you can identify them on this chart. So the recall is the percent of how many true positives, so actual positives for the binary, were predicted as a positive. And the specificity is just the inverse of that. It's the percent of how many true negatives were predicted as negative. And the precision is pretty much the inverse of recall. It provides a percent of how many positive predictions were actually positive. And the accuracy is really simple. That's just a percentage of predictions that were accurate to the actual value. And here's how you find each of those values on the summary reports. Your recall is going to be in the recall column at row 1. Your precision is in the precision column at row 1. And your specificity is in the recall at row 0. And all of this is provided in the code, so that's pretty easy to remember. Here's how you want to evaluate your binary logistic regression or any other binary classification model. You will look at the specificity and the recall to see if they are both high and that they are similar in value. Here, they are literally as far apart as they can possibly get, 1 and 0. So the model has not done well. But if you wanted to go further, you could move on from your balance of recall and specificity and look at your precision value and see if that's high. And finally, you would go down to accuracy to see if it's high. And that is in an order of importance. If your recall is bad, if your recall and specificity balance is bad, but your other values are good, it's still a bad model. It's still a bad model because that balance is the most important aspect. And here, you can even see that in an example because the accuracy is 97, which seems really good. But here's the problem. It looks like it just classified everything as 0, aka not being in the Bronx. So that's really not helpful, is it? But yes, that's pretty much how you would evaluate the output of a binary logistic regression, but a multinomial one's going to look a little bit different. So again, multinomial meaning you can categorize into several categories at once instead of just a binary if something is true or not. So here, we know we have our X and Y again, all that. And I have to do some imputation, basically replacing some null values. But that's specific to this data because it wasn't completely clean. And again, this shows the analysis process is iterative. You'll often come across things that should have been done earlier that you only find out about later. So you just have to get used to that if you're going to do this kind of work. It is not linear. Granted, most things are not linear. Right. So I split the data again, and the only difference in coding a multinomial logistic regression and a binary one is that the multinomial one will require this parameter. Multiclass is multinomial. If it's binary, you simply don't include it. And that's pretty much it. There are other parameters, but what each of those parameters do is fairly complex, and it's a little beyond the scope of what we're trying to teach here. But for pretty much any model that you get, you will have a series of parameters that will influence how well it performs. But here, I'm just going to run the multinomial logistic regression to see if we can predict the neighborhood well based on a series of inputs. And as I generate that, you will notice that our report looks a bit different. We no longer have that 0 and 1 for each thing, which means that we can't find the specificity. Well, if you can't find the specificity, how do you analyze this? How do you see if it's good? Well, here's how. You look at your recall column, and you see if they are all balanced and high. So are they similar values? And are they high, which is usually considered to be at about like 0.75 or higher. Here, none of them are high, and they have a pretty huge range between 0 and 64. So it hasn't done well on that front. And that is the most important factor for determining how well multi-class classification problems have performed. But if you needed to go further and analyze the model, you would see each individual precision value and see if those were high. So you're not comparing them to one another, you're just seeing if they're all high. And in this case, they're not. But whatever, we kind of knew that that was probably going to be the case. And finally, you would go into the accuracy. And again, this is an order of importance. If you see that your recall balance is bad and that there was a low value, you usually don't even have to look at the other metrics, because that is the most important thing. And accuracy really isn't all that important to us. And that's pretty much how you would evaluate a multinomial classification problem. Now, one thing that's important to note for machine learning purposes as we go into the next class is the summaries that you have seen are not exclusive to linear and logistic regression. So, for instance, if you look at this output would occur for any multi-class classification problem that you have, regardless of the model that you use for it. Because they're all analyzing the same thing. How well can we predict the category of this thing? And these are the statistics that are relevant for that. So it doesn't matter what kind of model you use, so long as it's doing the same thing, because it'll provide the same output. And that's true also for our linear regression. So again, this is pretty much just trying to predict a numeric outcome, and there are several models that can predict a numeric outcome. So any model that does regression is going to have this statistic set. So you have your classification problems and your regression problems, multiple models apply to both, but they'll all come out with the same statistics, which makes it easy to compare how well models have performed and see which ones you should use. Right? Because say, if we go back to the example for Airbnb, we want to provide a price that we would suggest based on, say, like the square footage of the place, what kind of place it is, where it is, etc. We might not get a good result with linear regression, but if we run it with k-nearest neighbors, which is a different model and works a bit differently, then we could use that model instead to make that prediction, assuming that it can make that prediction well, which isn't always the case. There are some cases where the data is just so varied and so random that no model is going to work all that well with it. But you never know until you try multiple models. But that's pretty much everything that I have for linear and logistic regression. Again, you can run a model to try to find the value for unlabeled data. So try to categorize data that doesn't have a category already, try to predict a value that the data doesn't have already, etc. Or for linear regression, you can use a statistical output to see which variables you should consider, because it'll show you exactly how each of those values impacted your outcome and see if the variables in aggregate will impact your model in any meaningful way, any consistent way. But that's basically how each of these things work. Of course, they have their own mathematics behind them, but again, that's beyond the scope of this. But that's basically how it works in Python and what you can expect to see once you run these models. So, any questions about any of this or for other models or anything like that? Other applications?
Yeah, this is pretty good
Mhm.
models. Yeah, logistic and the multinomial, they are very good, I think, the regression models. I'm just doubting. I think I have used for this regression the SPSS, the statistic model, IBM, I think. So what is the difference between this Python and that SPSS model to the regression analysis? The results are similar, or which one is better? Do you have any idea or suggestion?
I'm not familiar enough with the other program to know for a fact, but the thing is, linear regression is going to have the same formula no matter what program you're running it in. So I don't think it would make a difference, so long as they're both running linear regression.
Okay, yeah, that's great.
And same thing for logistic regression. The only thing is that if you're running models as opposed to those statistical summaries, your model will change slightly depending on the data that you feed it.
Yeah.
Because it's going to learn a little bit differently depending on what data you give it. And that'll make slight differences in how well things perform. And that's more noticeable in logistic regression, but that's more for the machine learning class. I'll explain more about how you can fix that later on.
Yeah, thank you very much.
Yeah, it's no problem.
Yeah.
So how are we doing, Ryan? Anything? All right. Well, that's fine by me. So I hope you all have a good spring break. Everything will be
Thank you very
posted.
much.
This will be posted on YouTube. The files, I know I sent
Yeah.
them in email, but they will be on the website. Also,
Mhm.
just people need to access them through that. But yeah,
Mhm. Very good.
everything will be available.
Yeah, thank you very much.
Yeah, no problem.
Yes, and Max, I just want to request, like last time also I have requested, we have around like 25, 30 people probably. Yeah, so we'll discuss like at least one class, regarding all
Mhm.
these machine learning or regression or what kind of data analysis tools are there, just basic overview.
Mhm.
We'll not go in detail. And if they are interested, then they can register and go, like as you have all
Mhm.
these things, they can go. But overall, we'll just tell them that here, hey, there are some models that if you want to learn, you can
Mhm.
approach. So just to give some kind of guidance. So if you are available in persons, that would be better. That would be great. If not, we can do the Zoom link. So there will be around 20 at least the people who
Okay.
will attend your session. So that we will discuss in detail after spring break, or we'll
Yeah.
just figure out the timing. So that would be great, I think.
Yeah, that sounds interesting. Very
Yeah,
interested in that.
yeah,
Yeah, there are a lot of different kinds of models, so we can even talk
yes,
about that.
yeah, yeah,
Like some
right.
of them work just like with pure math, like
Mm.
these regression tools that we've seen here.
Mm-hmm.
Others are a complete black box.
Yes,
You don't understand a single thing that they're doing other than like the physics.
exactly, exactly. Yeah.
And then
So,
others will work well with certain kinds of data, but it won't work at all with others, that kind of stuff.
mhm.
So it
Yeah,
really does change quite a bit model to model, which is
yes,
why
yeah.
we run several of them to see how they're working.
Yeah, that's great.
Mhm.
Yeah, thank you very much for your time, Max.
Mhm. Always a pleasure.
Yeah. Have a nice spring break then.
You too. You too.
Yeah.
All right. I'm gonna sign off.
Yeah, thank you very much. Have a nice time. Take care.
You too. Goodbye.
Goodbye.